Hi everyone, welcome to my YouTube channel. If this is your first time here, then I'm so happy you found me today and I hope you come back soon enough. So in this video, we're going to be predicting medical insurance costs using linear regression. So linear regression in the context of machine learning is just a method used to understand and establish a relationship between two variables. Although this is not just all about linear regression, but at least that's the basic concept of linear regression. I would like us to pay attention to an example that I'll be showing shortly because it just gives us a basic picture of what linear regression is all about. Trust me, linear regression is one of the simplest machine learning algorithms in the context of machine learning. So if you can grab the basics, then um, you'll be able to build complex models using linear regression. Suppose you have a class of students and you want to understand how the number of hours studied affects exam scores. You plot a graph where each point represents a student. The horizontal axis shows the number of hours studied and the vertical axis shows the exam scores. Linear regression is like trying to draw a straight line that best fits all these points on the graph. This line represents the relationship between study hours and exam scores. Once you have this line, you can use it to make predictions. For example, if a student studies for, let's say, 4 hours, you can look at where 4 hours meets the line on the graph and predict their exam score. So in this case, this is where we have the 4 hours here. All you need to do is move up from here down to where 4 hours meets this red line and move straight down to the left. So in machine learning, algorithms are used to find the line that has the best overall distance from all the points. This is known as the best fit line. Linear regression assumes a straight line relationship between variables, but then in real life relationships can be more complex. So while linear regression is a good starting point, it may not always provide the most accurate predictions, especially in cases where the relationship isn't linear. And of course, you're going to agree with me on this. So, what are we trying to say? Linear regression in machine learning is a way of projecting one variable, like for example, exam scores in this example, based on another, that's study hours in our case, by finding the straight line that best represents their relationship. So if you pay attention to this graph, you'll see that each blue dot on the graph represents a student. The horizontal position of the dot shows how many hours the student studied, and the vertical position shows their exam score. Now the red line here is the result of linear regression. It's the best fit line that tries to summarize the relationship between hours studied and exam scores. The line was calculated by machine learning model to have the least overall distance from all the blue points. So if you see here, you would see here that if you pay attention, you will see here that this line, the way it is now, it's done in such a way that it has the least overall distance from all these blue points here. So if you want to predict the exam score for someone who studied, say, 3 hours, you would still do the same thing we did in the case of 4 hours. So you will find the 3 hours on the x-axis, that's the horizontal, move straight up to the red line. Then from where you meet the red line, you move to the left to meet the y-axis. I don't know why my mouse is acting up, but so when you get up here, you move down to the left to where you have the y-axis. The point where you made the y-axis gives the predicted score. So you see, this graph visually demonstrates how linear regression in machine learning works by establishing a relationship, in this case between study hours and exam scores, and using it for predictions. So that's just the basic concept behind linear regression. The dataset used for this project is a popular dataset found on Kaggle, and we'll be using Jupyter Notebook to run our codes. So in a short while, I'll be showing you the dataset, but first of all, let us import the relevant libraries that will be used in this project. At this point, we have imported the libraries we would use to read and manipulate the dataset and also carry out some visualizations. We've also imported train test splits and linear regression, which we will use to train our model. Let us go ahead and read this data so we can see what it looks like. So I'm going to create a variable which we'll call df. This dataset, as we can see here, contains 1338 rows and 7 columns. So we've got information containing the age of the client, the sex, that's whether they identify as male or female. We also have BMI, which I'm going to explain shortly for those who are not conversant with the term BMI. From the data, we would know if a client has kids or not. If they do, how many kids do they have? We also know if they smoke or not, and then the region from where they are from, and of course the column of interest, which is going to form our target variable, the charges. Everything seems very straightforward except the BMI. So let's have a look at what BMI really is all about. Your BMI can be calculated using your weight and height. So on the screen is the formula, that's weight in kilogram over height in meter square. So for example, if you are, let's say, 175 cm in height, which is 1.75 meters, and you weigh 70 kilogram, so that means your BMI is going to be 70 kilogram over 1.75 meters square, and that will give you 22.85. If you pay attention to the screen, you would see sort of an illustration to figure out from your BMI if you are underweight, if you have, if you are normal weight, overweight, or if you are even obese. So you can see here that for the obesity class, we have three classes: class 1, class 2, class 3. Going back to the example we gave, so assuming your BMI is 22.85 kilogram per meter square, so that means you would be regarded as someone who has a normal weight. Now that we have a basic understanding of what BMI is all about, let us see if we can, have a look at our data to make sure that our data is in line, and we won't run into problems while we are building our machine learning model. So for this, we'll be using the info function to at least see the properties of our data. So right here we can see that we've got 7 columns. We don't have any columns containing null values. The age column is set to integer, and we can see here that we've got the BMI set to floats, and so we can see here that everything looks good. So at this point we're going to be looking at some statistic information of our data. So for that, we're going to be using the describe function. So usually when you use the describe function, you would be able to see basic statistical information about your data set, and sometimes it can help you spot out some issues or problems that might be wrong with your data. So for example, if we look at the age, we can see here that the mean age, that's the average age, is 39. The minimum age here is 18 and the maximum is 64, which makes a lot of sense. For example, if we had seen an age of say a maximum age of 200, then we would know that, oh, something is wrong with this data set, because I don't think anyone would, it's very unlikely to see someone who would live up to 200. So the same thing with the children. So we can see here that the minimum is 0, meaning that some clients don't have kids in our data set, and the maximum is 5. So there are no funny looking figures on the part of the children. And we can also have a look at the charges column to see if to have an idea of what our data is telling us about. So it's not just about, the truth is that it's not just about looking out for irregularities or any of that. It's also good to use the describe function to have a general overview of your data. So at this point now, we know that the average charges is 13, the average charge is 13,270, and we have the maximum, a maximum charge of 63,770. So I'm not sure why this customer was charged so high, but at the end of this project, things will become clearer to us. Let us go ahead to find out more about our data set. So we are going to be plotting a histogram now to see the distribution of age of the ages in our data set. So right here, we have a graph showing the distribution of age. So if you pay attention to this code, you would see here that we just plotted a histogram. We assigned the horizontal axis to be age. We're using 47 for n pins, and that's the number of bins, and we've assigned a title to this histogram called distribution of age. So we have something interesting right here before us. We can see here that most of these clients fall within 20 to the maximum age, which we've already seen when we're looking at the statistical information of our data. But then we've got a large number of people who fall within 18 and 19. So we're assuming that this this company only takes in adults starting from 18, but then we can see a huge spike here showing that majority of the people who are in this company fall within are actually teenagers. So maybe we can assume here that there is some sort of special discount that encourages people who are teenagers to enroll with this company. So next, we are going to be looking at, let's have a look at the distribution of sex in our data set. So we're going to be using green and orange to distinguish between male and female. Let's set the size to be 8 by 8. So from this we can clearly see from this pie chart that the sex is evenly distributed in our data sets. So the ratio is almost 50-50. 50.5% of the clients in our data set identify as male, while 49.5% identify as female. Next, let us look at the distribution of BMI. Since it's almost same codes, we're going to almost same codes we used in the distribution of age. Let us just copy this and make some changes to save time. So on the x-axis, instead we're going to be looking at the BMI. So we'll edit this to BMI. Change the title also, distribution of BMI. What else we can do is that we can add a color discrete sequence to it. So in this case, we'll be using green. We'll be setting this to green. I think that's about it. Sorry about that. I should have added a comma here. Right. So we have the distribution of BMI. So you can see here that this is actually a normal distribution. This is a term used in statistics to, when you plot a graph, You could start from low, and then you have something that looks like a high rising building, and then a fall as you move to the right on your graph. So this is termed a normal distribution in statistics. We can see here that a lot of these clients fall within the range of having a BMI of say 25 down to 33. So what do you think, judging from the picture that was used to explain the BMI, the concept of BMI, would you say that most of these clients are normal weights, overweight, or underweight, or could they be obese? I would leave that to you to figure out. So I would suggest that you pause the video and try to figure out on your own using the you can rewind this video to have a look at the picture and then try to see if you can make some sense out of the distribution of BMI. So at this point, I would suggest you pause the video. Now let's go back to that picture. Considering that a lot of these clients have BMIs ranging from 25 to 33, we would say that most of them fall within the range of being overweight to obese. So you can see that huge spike. When you look at the graph, you can see that huge spike showing that a lot of clients actually fall within overweight to obese. But then few of them actually fall within the range of being underweight if judging from the distribution of BMI. Next, let us take a look at the distribution of charges, which of course is our main point of interest, considering that the charges column is going to be our target variable. Just similar to what we did the last time, to save time, let's copy from the distribution of age, paste it down here. So in this case, the x-axis is going to be the charges. We'll change the title to distribution of charges. However, let's do something interesting here. We want to see, we want to color this graph by the smoker column. So what else can we do here? Yes, we can use a color discrete sequence to identify who is a smoker and who is not. So we can set red for smokers and green for non-smokers. I'll need to rearrange this code. Sorry for the error. So let us take a quick look at this graph showing us the distribution of charges. So I'm going to give you, if you want, you can pause the video so that you can see if you can make some sense out of this on your own. Okay, so I assume you've paused the video to make sense out of it. Now we can see here that a lot of people are actually charged, say from 10, let's say from 12,000, around 12,000 and below. But then we can see here that people, we have quite a few people who are charged 20, 30, 40, 50, 60 and the rest. But then because we were able to specify in our graph who is a smoker and who is not a smoker, we can see clearly here that most of the smokers fall within the range of, most of the smokers pay more than £40,000. So you can see here that virtually almost everybody who pays more than £40,000 is actually a smoker. But then we have few others who are paying up to 20k who are not smokers. But then you can see here that there's a clear distinction if you look at the if you glance through this graph from mere observation. You can see here that most of the high figures are recorded by those who smoke. So you can see here that even without plotting a correlation map, you can see here that smoking actually has an impact on the charges of the way charges are distributed among the clients, and which actually makes a lot of sense because when you smoke, there is a high tendency that you might need to go to the hospital at some point due to the health related risks of smoking. Now that we've plotted some histograms to see the distribution of some of the columns in our data sets, I think at this point we should try to compare the future variables against the target variables. So in this case, we are going to be, at this point, we're going to be plotting a scatter plot. We're going to be doing a scatter plot to see how the ages in our data set relate to the charges. Or rather, I would say the relationship, like just to have a pictorial view of the relationship that exists between age and charges. So we're specifying that we want the ages on the x-axis and we want charges to be on the y-axis. We'll set opacity to be, say, 0.8. And we'll set the title to be age against charges. So we can find something interesting here. So by plotting age against charges, you would agree with me that it seems that from our graph, it seems like the older you get, the older you are, the more charges, the more likely it is that you're going to be charged higher than people who are younger than you, which of course makes a lot of sense because when you grow older, your body becomes weaker. So it makes sense for the insurance to charge you higher than people who are younger than you. But then let us see if we can let us see if we can find an interesting pattern to see if we can see any interesting pattern with between the the age distribution and charges with respect to who smokes and who doesn't smoke. So let's just see if we can add that to our graph and see if we can uncover any hidden pattern in our data set. So we want to see a way we can identify smokers and non-smokers, and we'll be adding a color discrete also, a color discrete sequence. In this case, we want red to identify smokers and green non-smokers. So at this point, let's see what we will discover. So we've run into an error here, and that error is due to a typographical error here. Interesting. So we can see here that despite the fact that the older you are, the more charges, that pattern exists even for smokers. So the older you are, it seems like the older you are, yes, of course, there are more charges, but then there are more charges for even older people who smoke compared to younger people who smoke. So right now we're already discovering patterns, interesting patterns in our data set. But however, by the time we carry out more visualizations and try to drill through, especially when we have a look at a heat map showing correlation, things will become very much obvious and clear to us. We will do the same thing we did here for age against charges for BMI. Let's say the relationship between BMI, the relationship that exists between BMI and charges. So we're setting X here to be BMI, and we're editing the title also. Oh, sorry, this should be charges. So we're saying BMI against charges. So right now we're going to run this code, and you see we can see something interesting here. Remember, we've been able to identify smokers and non-smokers, to distinguish between smokers and non-smokers in our visualization considering the BMI against charges. So you can see here that for people who do not smoke, it seems like there's no much cordial relationship between. So let us try something. So I've turned off the smokers. We can only see the BMI for people who do not smoke. So you can see here that the data points are scattered all over the graph. There doesn't seem to be much, direct relationship between how much BMI that is your BMI and how much you're charged. So we can see data points scattered all over. But then when we toggle the smokers off, we can see here that there seems to be a pattern between BMI and charges for people who smoke. So it seems like if your BMI is below 30 as a smoker, there's a possibility that you will be charged a certain amount from, say, between 10k to, say, 32k or thereabout. But then, however, the higher your BMI as a smoker, the more charges are going to be incurred on your part. So we can see here the relationship. And of course, this is another indication of the role that smoking has to play on your medical charges. So we'll just turn it back on so it stays the way it should. Let us plot a heat map that would show the correlation between all the other variables against all the other variables, that's the future variables against the target variable, which is the charges. But before that, let us pay attention to our data set again. We can see here that we have three columns that exist as strings, that have data existing as strings, and that's the sex, the smoker, and the region column. So in order for us to create our heat map, we will change the values in these columns into integers. But first of all, I would like us to carry out some investigations on the region column so we can understand how many regions are there and what regions. So after using the unique function, we can see here that we have 1, 2, 3, 4 regions. That's the southwest, southeast, northwest, and northeast. We will use this information while converting our strings into integers. Let us start with the smoker column. I forgot to add the equal sign here. So what we've done here is that we've specified that wherever we have yes in our smoker column, yes should be assigned the value 1 and no should be assigned the value 0. So at least this will help us to build our heat map. So we're going to do exactly the same thing with our region, just similar to what we've done with the smoker. So wherever we have southwest, this should be assigned the value 1. We'll do exactly the same thing for the sex column. So we've done exactly that. So for our smokers, yes will be designated 1, no will be designated 0. And for the south, for the different regions, we have 1, 2, 3, 4 for the different regions, and 1 where will be designated to the male, to people who identify as male, and 2 will be designated to people who identify as female. We will go ahead and plot our heat map now. And we're assigning the fixed size to be, let's say, 12 by 8. At this point, we have our heat map here. But then it seems we are missing the smoker column. So let's find out what's wrong. Funny enough, we're actually missing all three columns. There's the smoker, region, and sex. Let us look at our dataset one more time. Okay. So you can see here that the changes are not yet reflected. So you can see here we have sex none, smoker none, region none. So at least that is a good start in trying to debug errors associated with this type of problem. So we're taking it off. Considering that the data might have been overwritten, considering that there might have been an overwriting issue while running our codes, what I've done is that I went straight back to run the to reread the CSV file into our project, and of course assign the variable df to contain that CSV file. And I've also come down here to rerun this code here, this block of code, so that if we call our data back in, if we call the variable back in, okay, so the error still persists. So if you encounter such an error, then probably there might have been a data overwriting issue on your code. So you can see here that the issue has been resolved. So what I did was that I reran the code to bring in the data set just to take care of any data overriding issue, and then the machine takes note that okay, you've got your data sets in this variable df. So while doing yours, while carrying out similar projects, if you run into something, if you run into an error like this, all you need to do is probably restart and run all to override any data, to correct any data overriding issues. So it seems like the problem has been resolved now. So at this point, let us create our heat map again. So we're specifying that the fixed size should be 12 by 8. We want to use the purple color. The we want to use color purple as our color in the heat map. So you can see here that we are back on track now. So sometimes while you're coding, you might run into similar issues. All you need to do is retrace your steps and try to fix those errors. So if you look at this heat map, you would see that the first of all, take note that it's the color is purple in our on our heat map. So wherever we see darker colors, that darker purple colors, you will see, it would interest you to note that those areas show very strong correlation. For example, let's take age. Or okay, we're interested in charges, so let's take the charges section. For example, you can see here that while comparing charges to charges, if you plot a linear graph to compare charges against charges, you will get a very straight line graph. It's going to show a very strong linear relationship because obviously you're comparing charges against charges. So charge 5 is going to be equal to charge 5, charge 10 is going to be equal to charge 10, whatever it is. So that's why the charges here shows the charges against charges shows correlation of 1. So usually you would have a correlation between 0 and 1, and 1 indicating very strong correlation, and that's why we have a very dark purple color here. If you glance through the heat map, you will see that some areas appear to be lighter. The purple appears to be lighter. These are areas that have weaker correlation. But then our target variable is the charges, so we're going to be comparing charges against the other variables. Let us start with smoker, which appears to have a dark purple color, but not as dark as this one here. But then it shows that it has a strong correlation, and you can see here that the correlation here is 0.79. So if you compare it with something like the region, you would see here that the region, the color here is almost getting towards white, because if you look at the key, if you look at this area here, you would see here that from 1, the color progresses down to almost white. So you can see here that region has a very low correlation, so of 0.0062, so it might not really have any much impact, or I would rather say it doesn't have any much impact on how much you're going to be charged. So your charges might not depend on your region exactly, so it wouldn't make any sense to include this in the model that we are going to build very soon. So you can see here that smokers has a very high correlation, which makes sense from the other graphs that the other visualizations that we've done in the past, showing the relationship between smoking habits and charges. We can also see here that age has a relatively high correlation too, but not as high as smoker, considering that it is having a correlation of 0.3. The good thing about heat maps is that you might not really have the time to glance through all the figures. All you need to look at, all you need to pay attention is the progression of the color, how dark or how thick the color is, depending on what you are after. So from this heat map, I think it would make a lot of sense if we include smoker, the smoker column, the age column, the BMI having a correlation of 0.2, and perhaps the column containing number of children. At this point, we will be dropping the sex column and the region column, considering that both columns have show very weak correlation. At this point, I will assume that we are in another stage of the project altogether, so it would make sense if we specify a heading here, and we can call this model training and testing. Good. So we're splitting our data now into X and Y, and the X is going to contain our feature variables, which we've already said, which we've already agreed on using age, BMI, children, and smoker. So we have our Y containing the target variable, which is going to be charges. There's a typographical error here. Train test split. So right here we are specifying that we would like 30% of the data set to be used for testing, and that's why this is 0.3 here, and 70% of the data set will be used for model training. On this line of code, we are creating an instance of the linear regression class. So this line initializes a linear regression model. This line of code here that has been highlighted trains the linear regression model using the training data So the fit method finds the coefficients of the linear equation that best fits the training data. While this line of code here, so after training the model, this line uses it to make predictions on the test data. So the predict method applies the the predict method here applies the linear equation to the test data to output the predicted values of the target variable. So these are predictions are stored in the variable pred. So at this point, let us import R2 score, which we can use to evaluate the model. Right now, we have used the R2 score to evaluate the performance of our regression model or linear regression model, and we can see here that this model has an R2 score of 0.76. Why don't we create a data frame that we can use to, let's say we have information of a client, and this client, we have their age information, BMI, whether they have children or not, how many children they have, whether they smoke or not. So let's see if we can use this model that we've built to find out how much the client is going to be charged based on the information provided. So let's create a variable here named test, and we can put some information in a dictionary about the client. So let us imagine the client is 33 years old and the BMI is 23. The client has 4 children and the client is not a smoker. The client doesn't smoke. So assign this to be 0. We'll set the index to be 0. Now that we have this information, let's convert this into a data frame. So we're converting the data stored in the variable tests into a data frame. Then finally, let's see what this data frame looks like. So this is what the data frame looks like. So we've got age 33, BMI 23, client has 4 children, and the client doesn't smoke. So let's predict how much. Let's let our linear regression model tell us how much this client is going to pay for medical insurance charges based on the information that they have provided. So we can see here that based on this information, the cost of medical charges, insurance charges, is going to be 5,572. Of course, this currency could be in pounds, dollars, or whatever currency, euro, whatever currency that is involved in a real life situation. So now that we know this, let us try to play with this data, this information. So what if the client is a smoker? Let's just imagine that the client is a smoker and we change this 0 here to 1, indicating that they smoke. What do you think would happen? I'll leave that to you to guess. Okay, so I'm assuming that you guessed right. Of course, the charges will go up 29,198. If you remember, smokers have the when we plotted the heat map, you would recall that the smoker column had a very high correlation. So let's set this back to 0. Let's assume that the client doesn't smoke. But then let's imagine that this client is, say, 60 years old. Okay, you know what? Let's set it back to the original, what we had before, 33, and then 0. So you see, we have our former charge here, 5,572. So let's say the client is 60 years old. What do you think would happen to the medical charges? Do you think it would go up? Do you think it would remain the same? Or do you think they will be charged less? And of course, they are being charged higher, 12,642. So at this point, I would say we are done training our machine learning model, and we've also looked at the practical application of this model in predicting the insurance cost for clients. So if there's any question you might have to ask, please leave that at the comment section. Or if you feel that I might have done something that doesn't look really right, you are of course welcome to share your views on this. So thank you very much for sticking with me from the beginning of this project to the end. I hope to see you in my next video. Thank you very much and have a nice day.